Optical amplification, boosting signal strength for longer distances. Optical amplification, boosting signal strength for longer distances. In the world of telecommunications, optical amplification refers to the process of boosting the strength of a signal transmitted through fiber optic cabling. This is important because over long distances, the signal can weaken to the point where it becomes unusable. Fortunately, there are several different types of optical amplifiers available, each with its own strengths and weaknesses. Before diving into the technical details, it's important to understand why signal strength degrades over distance. This phenomenon is known as attenuation, which is the loss of signal strength as it travels through a medium. In the case of fiber optic cables, attenuation is caused by a number of factors, including absorption, scattering, and bending losses. Essentially, as the light travels through the cable, it interacts with the atoms and molecules of the glass fibers, which causes some of the energy of the light to be absorbed or scattered. To combat this attenuation, optical amplifiers are used to boost the signal strength at regular intervals along the fiber optic cable. As the signal travels down the cable, it will naturally begin to weaken, but each time it is amplified, the strength will be restored to its original level. This allows for longer transmission distances without sacrificing signal quality. There are several different types of optical amplifiers available, including erbium-doped fiber amplifiers, semiconductor optical amplifiers, and Raman amplifiers. Each of these technologies has its own unique benefits and drawbacks, which we will explore in more detail below. Erbium-doped fiber amplifiers. Erbium-doped fiber amplifiers, EDFAs, are the most commonly used type of optical amplifier in long-distance telecommunications. These amplifiers work by doping a length of optical fiber with erbium ions, which can be excited by pumping them with light at a specific wavelength. When this happens, the erbium ions release energy in the form of light at a higher wavelength, which is in turn amplified by the fiber. One of the key benefits of EDFAs is that they can be integrated into the fiber optic cable itself, which eliminates the need for separate electronics. This makes them ideal for long-distance transmission, as it reduces the need for frequent maintenance and troubleshooting. Additionally, EDFAs have a broad amplification range, which means they can amplify a wide range of wavelengths simultaneously. Why? However, EDFAs also have some limitations. One of the biggest drawbacks is that they are sensitive to changes in temperature, which can affect their performance. Additionally, the amplification provided by EDFAs is not constant across all wavelengths, which can cause problems in certain applications. Semiconductor optical amplifiers. Semiconductor optical amplifiers, SOAS, are another type of optical amplifier that are used in telecommunications. These amplifiers work by using a semiconductor material, such as gallium arsenide, to amplify the signal. SOAS are typically used for optical signal processing and regeneration, rather than long-distance transmission. One of the benefits of SOAS is that they can be integrated with other semiconductor components, such as lasers and modulators. This makes them useful for applications where space is limited, such as in fiber-to-the-home (FTTH) installations. Additionally, SOAS have a high modulation bandwidth, which means they can amplify signals with rapidly changing amplitudes. However, SOAS also have some drawbacks. One of the biggest limitations is that they can saturate quickly at high power levels. This means that they are not well suited for long-distance transmission applications, as they may not be able to provide enough amplification to overcome attenuation. Additionally, SOAS are sensitive to changes in temperature and can suffer from chromatic dispersion, which can cause distortion in the signal. Raman amplifiers. Raman amplifiers are a type of optical amplifier that work by using a nonlinear phenomenon known as the Raman effect. This effect causes photons to scatter off of molecules in the fiber optic cable, which can be used to amplify the signal. Raman amplifiers are typically used for long-haul transmission applications, as they can provide high gain over long distances. One of the benefits of Raman amplifiers is that they are not temperature sensitive, which makes them ideal for long-distance transmission in harsh environments. Additionally, Raman amplification is wavelength independent, which means that it can amplify signals across a broad range of wavelengths. However, Raman amplifiers also have some drawbacks. One of the biggest limitations is that they require a high pump power to achieve the desired amplification, which can be expensive and require frequent maintenance. Additionally, Raman amplifiers are not suitable for amplifying signals at very high speeds, as the Raman effect is a relatively slow process. It's worth noting that ongoing research is being conducted to improve the performance of current optical amplification technologies. For example, there are efforts underway to develop more efficient and less temperature-sensitive EDFAs, which could make them more suitable for a wider range of applications. Additionally, new materials are being explored for use in SOAS, which could improve their performance at high power levels. Another area of active research is in the development of new types of optical amplifiers. For example, there are efforts underway to create all optical amplifiers that can amplify signals without the need for any electronic components. Finally, it's worth noting that optical amplification is just one of several technologies that are used to enable long-distance telecommunications. In summary, optical amplification is a critical technology that is essential for enabling long-distance telecommunications. By boosting the strength of the signal at regular intervals along the fiber optic cable, it is possible to transmit data over much longer distances without sacrificing signal quality. As the demand for high-speed, long-distance telecommunications continues to grow, the importance of optical amplification cannot be overstated. By addressing the issue of attenuation, optical amplifiers allow for the transmission of data over much longer distances than would be possible otherwise. One potential application of optical amplification is in the development